Good morning, everyone. On behalf of the International Finance Corporation, the IFC, the branch of the World Bank Group that focuses on supporting the development of the private sector in emerging markets, I want to welcome you, all the attendees, and we hope that you and your families are all good and in good health in the current circumstances. Thanks for joining this hopefully interesting discussion. I am Carlos Serrano. I'm talking from our Mexico office. I am the program manager for IFC Green Banking Academy. Our program provides financing, advisory, and knowledge sharing to the financial sector around the world and in Latin America. And we accompany the transformation of banks from business as usual to sustainable and responsible banking. One of our main priorities is promoting climate change and climate finance to fight climate change. It's not that we are promoting climate change, but climate finance to fight climate change. We have launched a series of webinars open to the market under the title Ctrl+Alt+Delete Green Revolt. What do we mean for that? Control means that we can control the future of the world. We all like to live in. Alt stands for there are better alternatives to what we are doing at the moment. And delete means that we can erase the mistakes of the past. So today we are proposing a reboot. This is an opportunity for a green rebuild. This is the second webinar of the several that we will be holding every week going forward. Let me explain some logistics. We have a schedule of around 25 to 30 minutes for the presentation that will be followed by 10 to 15 minutes of questions and answer. And if there are many questions, we might perhaps extend the webinar to whoever wants to stay for another 10 minutes. If you have any question, I can ask you to please post them in the section for question and answer, which is on the right side of your screen. Let me explain now a little bit about the specific goal of this webinar. The main objective is to discuss the connection between the most recently discovered elementary particle, the Higgs Boson, and the crisis generated by the coronavirus and a more sustainable world, and understanding that climate change is also a 200-year-old basic science. This is a discussion about the benefits of fundamental research in a world that until now has been driven mainly by short-term sight and short-term returns. Professor de Rújula will take us through the journey of understanding the real value of fundamental research. And he will do it in a language that all of us, hopefully, we can all understand. Investing in basic science is always one of the two best possible investments, but sometimes it is in the medium, long, or very long term. I'm going to present now our special guest, Professor de Rújula, that, as most of you know, he's one of the most important theoretical physicists in the world. And since 1977, he has worked at CERN, the European Center for Nuclear Research in Geneva, Switzerland. He was born in Madrid, where he studied physics and obtained his PhD at the Complutense University. He has worked in Italy, ICTP Trieste, France, AHIS near Paris. In the United States, he worked at Harvard and Boston Universities, Massachusetts Institute of Technology, and at CERN, he had diverse roles, from summer student to leader of the theory division. More recently, he works at the Institute of Theoretical Physics of the Autónoma University in Madrid. De Rújula is amongst those who try to understand elementary particles and the fundamental forces between them, as well as how these entities have determined the evolution of the universe as a whole from its beginning. In the 70s, he contributed to the consolidation of the standard model of particle physics, in particular to the study of quantum chromodynamics, charmed particles and their predicted masses. He has worked in many other fields, such as X-raying the Earth with neutrinos, measuring the masses in the lab, searching for antimatter in the universe, understanding cosmic rays and gamma-ray bursts, and the development of the methods that contributed to the discovery of the Higgs boson. Álvaro has recently published the book Enjoy Our Universe, You Have No Other Choice, in Oxford University Press. And let me share a secret with you. The drawings that you are going to see during Alvaro's presentation today have been drawn by him. So on top of being a leading physicist, Alvaro is also an artist. Alvaro, welcome to this webinar, and the floor is yours.
Thank you very much. I hope you can hear me, and I also hope you can see the screen, which is now red, and it says test. Is that correct?
Correct.
Thank you very much for your introduction, a very generous one. And thank you to all of the participants, and good health to everybody. Now, since I am a scientist, I know that nothing ever works properly. So I have this test for starters. I hope the word test is coming out on the screen. Carlos, since the connections via webinars and things like that always disconnect the words from what you see, and it's so difficult to follow, I hope that if I am running too fast, talking too fast, you give me a warning telling me, stop, please, talking so fast. Now, I'm, as Carlos said, going to talk about the Higgs boson and the coronavirus. Now, this very peculiar title is hiding the real title, which is the role of basic research, that is the one that is knowledge-driven and not spin-off, fast dollar-driven, after the times of the pandemic, which is certainly a question that will be very much discussed. Now, let me start with a disclaimer, and that is that what I shall discuss reflects my personal views, not necessarily the ones of the institutions to which I belong or I have belonged. And since we cannot discuss such an enormous subject in so little time, I am going to employ the Spanish technique of offering you tapas. That is to say, a little bit of taste of this, a little taste of that, in a manner that you can then decide whether you continue eating something, like a discussion about the Higgs at CERN, and COVID-19 and genetics, or climate at CERN, and why basic research ought to be done. That's the plat de résistance. Now, the Higgs boson is an elementary particle, that is to say, a particle that, if it has constituents, if it is made of smaller things, we don't know. And its average lifetime is about 10 to minus 22 seconds. That is an American billionth of a trillionth of a second. Pretty little time. So what could be more useless than a Higgs boson if it doesn't last long? Now, in order to explain that, I am going to start by telling you a little bit what CERN, the European Organization for Nuclear and Particle Physics Research, is. The member countries you see here in dark blue, and CERN has a staff of about 2,300 people. That is the people who are paid by CERN. But it has a lot of users, people from external laboratories or universities that come to CERN to contribute to the experiments that are done here. And from its 23 member states, there are about 8,000 people. From Russia, which is not a member state, there are a bit more than 1,000, a few more from the United States, and from many other places, like China has 510 people here, more or less. Now, people at CERN come from 109 different countries, so it can be said that it is a pretty international organization. Now, CERN is located close to Geneva. Here in the lower part, you see the airport of Geneva, and dotted line is the frontier between France, which is to the upper part, and Switzerland, which is in the lower part. And things that you do not see but are added electronically to this picture, to this photograph, are accelerators that are underground, about 100 meters underground on average, And the largest one of them is called the Large Hadron Collider. Now, this is two accelerators in which particles that are atomic nuclei, such as protons, the atom of the nucleus of hydrogen, or heavier things such as lead, for instance, are accelerated in opposite directions, and there are 4 interaction points where they collide with each other. When this happens, new things that were not there before are created. The energy of the colliding particles is transmogrified, transmuted into the nature, into new things that come out of the collision. Each collision is called an event. Now, here's an example of an actual event, which is reconstructed by a computer, and you see these yellow lines are charged particles, and 2 lines in this particular collision are very interesting. They are called gamma rays, which is particles of light, but of very, very high energy. And on occasion, there are plenty of such pairs of gamma rays, but on occasion, a couple of them have the properties that define them as coming from a particle with a specific mass, which can be, and it is in this case, a candidate for being a newly discovered particle, in this case, a Higgs boson, that decays into many things, but among others, a pair of particles of light. What you see in here is not a picture of the discovery of the Higgs boson. It's a picture of one of the large collaborations at CERN celebrating the first collision. And you can see the picture is rather old because Chancellor Merkel looks pretty young in this picture. And you can also see that, like in other walks of life, you have everybody enjoying the moment, except the 2 that spent all the night before having everything ready for the collisions to be observable. Now, what do all these 20,000 or so people at CERN do? They do research, and they do it on the fundamental constituents and the fundamental forces of nature. And why do they do it? They do it because they want to know. And knowledge is something whose monetary value cannot be defined properly. Now, the Higgs boson, why should you care about a Higgs boson? Now, suppose that I take it away, this thing that was written there from the room, and in the room in which you are, you take the lights out, and you take all the air out, and you leave absolutely nothing. Well, you would, in this case, know that the room is still permeated by something that you cannot smell, or hear, or taste, or touch, or see, but of which you are definitely well aware. And it is the Earth's gravitational field which is holding you on your seat, assuming that you are still sitting down in that room. Now, suppose I throw you in a rocket to some place in the middle of nowhere in space where the gravitational forces are up to 0. It turns out that we know that there is something else there called the Higgs field, of which the Higgs boson is a vibration. And the Higgs field is uniform all over the universe, out there in space, and also inside you. So you are permeated by something that you cannot take away, which is this Higgs field. Suppose that I could take it away, which I cannot, but just for fun, I take it away. If there is no field, then the electrons would have no mass. And the electrons are constituents of the atoms of which you are made. So if the electrons were massless, they wouldn't be able to stick to protons, for instance, to make atoms. So there would be no atoms. And there would be no coronavirus as a consequence of that. You would have solved that particular problem. But if there was no Higgs field, there would also not be you. So you would have solved one problem too many. Now let me jump now to the spin-offs of basic research. Presumably the greatest one is due to this gentleman, Sir Tim Berners-Lee, who invented a so-called protocol, HTTP, Hypertext Transfer Protocol, which is the means by which he managed to have different computers of different groups of physicists talk to each other in such a way that they could, so to speak, understand each other. This was an idea that he had from childhood and which ended up being the World Wide Web. This the means by which we have now this revolution, which is the most important Pacific revolution, no doubt, since the invention of the printing press. Now, he didn't make a patent, and CERN did not make a patent, because it is a fundamental research institute, and everything it finds is supposed to be free for everybody. And that's why you have the web in its current status, in which you don't have, since it is not patented, to pay, say, $1,000 per megabyte transferred. If that was the case, then CERN would be the richest institution in the entire world. It could buy everybody. Now, there are many other things that you wouldn't suspect. For instance, a touch screen, whose roots also can be found at CERN. Now, I am to give you a warning and an apology, which is that I will space CERN results with results from other sources, also based in basic research. There are two reasons why I'm doing this. Reason number one is that I feel much better if and when I know what I am talking about. And reason number two is that other themes that I'll mention, for instance, molecular biology and genetics, are now even more obviously essential. Since I'm talking now about genetics, let me remind you that it all started with experiments by Mendel on pea plants and how their characteristics were inherited from one generation to the next, from which he found, first him, the rules of heredity. And to make a very, very long story with many characters short, I'll remind you of the other big step in this direction, which was Darwin's The Origin of Species, the theory of evolution. He began to understand how birds in different islands in the Galapagos evolved with time, adapting to the circumstances that they had to face. Now, another big step was made by Watson and Crick in 1953, which is the double helix DNA, desoxyribonucleic acid. You will know probably that you have inherited from your mother one of these strands of DNA, this helix, and the other one you have inherited from your father. And it is these two things put together in your genetic makeup, in your chromosomes, that make you have the potential to develop who you are. And these guys got the Nobel Prize, in my opinion, for simply one sentence in the article that they wrote. Let me read it. It has not escaped our attention that the specific pairing we have postulated immediately suggests a possible copying mechanism for the genetic material. Now, why I am saying that they got the Nobel Prize for a single sentence, which is quite a feat, that's because their results were based on previous data, mostly by Rosalind Franklin, obtained with X-ray crystallography, and by Maurice Wilkins. Now, I just put in a word, X-ray, that you all take for granted, but it's also a result of basic research. And we are now seeing how basic research, starting in the 1850s or so, has allowed us at the moment to study in detail the genome of the virus now in 2020. And this is clearly one of the serious weapons that we have in understanding and trying to solve this problem. Now, here is a picture of the damn beast, COVID-19. And I said picture and not photograph because it was made with an electron microscope. And how was it made? It was made with an electron microscope because it was understood from quantum physics, one of the great developments in science in the 1900s up to 1920 or so, and continuing. It was then understood that a particle, such as an electron, can also act as a wave. And an electron wave can be made to have a wavelength sufficiently small to disentangle the details that you see in this picture of a virus that could not have been taken with a light microscope. Now, it is a very, very peculiar and unpleasant thing for anyone, I guess, to be giving a talk to an audience that you do not see. So you have to imagine how the audience is doing at a certain moment. This is how I imagine you are at this moment when I am about 1/2 through my talk. That's to give you some hope that this will have an end. Now, suppose you have a set of walls in which you fill penguins in. You put penguins and penguins and penguins inside this fence. Now, penguins are objects that physicists call fermions, and they have the property that there comes a moment when you cannot add another one. But it was discovered by an Indian gentleman called Bose and by Einstein in 1924 or 25, that there is another way of packing things together, something that we physicists call statistics. You can pack ghosts, like in the lower half of the picture. You can always add one more ghost to this metro wagon, which is empty. Those particles that can be packed indefinitely are called bosons. And for instance, the particles of light, the photons, are bosons. And that means, among other things, that adding more photons in a particular state of energy and direction becomes easier and easier as you add another one. That's the basis of the laser. And the laser can be used, for instance, as you see in here, for therapy, for chirurgical practices. Now, in this very busy transparency, there are collected very many other basic things in clinical medicine that came from basic science. And for instance, X-rays gave rise, to, among other things, to computer-aided tomography, scanners. The antimatter, something extremely peculiar, is the basis of positron emission therapy. Nuclear magnetism gave rise to the scanners of magnetic resonance imaging, and so on, so on. Other things have to do with brachytherapy. Accelerators give you particle beam therapy. Lasers give you microsurgery, as I just said before. Polymerase chain reactions are the basis of forensic medicine. Penicillin, which was discovered by chance, certainly is important in the control of diseases. And the DNA structure, among other things, allows you to have gene therapy. Now, the interesting thing about the things written on the left of this slide is that each of these discoveries earned a Nobel Prize. This slide is not my slide. I borrowed it from a talk by Sheldon Lee Glashow, who also got a Nobel Prize with Steven Weinberg and Abdus Salam for one of the great advances in science of the past century, that was the unification of electromagnetism and the so-called weak interactions. Now, you may not know what the weak interactions are. They are, among other things, the reason for natural radioactivity. Thanks to natural radioactivity, we can study fossils or minerals from the past and understand climate as it was in the past. Another thing that depends on the weak interactions is the sun. The sun would not work if not because of the weak interactions. So if there were no weak interactions, there would be no sun, there would be no climate, there would be no climate problems. An interesting question to ask, I think, is how long did it take between a basic science discovery and the applications that come after it. We see in here, for instance, Mr. Newton with his supposed apple inventing the laws of motion, F equals ma, and the laws of universal gravity, which is what is written in a blob below. Now, the first practical application of the laws of motion, and in particular the law of gravity of Mr. Newton, was the Sputnik, the first Soviet satellite. And it took 271 years to go from the basic science to the first, let's call it, practical application. Now, from the equations written by Maxwell for unified electricity and magnetism and light, which is an electromagnetic wave also, I write them in here. They are pretty simple. I may even tell you what they are. The first equation tells you that an electric charge can create an electric field. If it is in motion, it can create a magnetic field. And if it is accelerated, it can create waves, for instance, the waves of light. The second equation says that there are electric charges, but there are no magnetic charges. So it's pretty simple, these equations. Now, William Hertz was the first one to exploit the fact that these equations predicted electromagnetic waves. He discovered the radio with this apparatus that, this is a picture that he took himself. And the distance in this case between the theory and the application was only 27 years. Now you know that when under pressure, some politicians rely on science or scientists. And then the elapsed times may be, sometimes hopefully, are much shorter. One classical example is Archimedes, who is said to have used mirrors to break the Roman siege of Syracuse. Now, apparently this is fake news, but it's anyway a very good story. Now, this is another thing which is not fake news, and you all recognize, and I will, of course, not talk about it. But since we're talking about someone that had something to do with it, here we have Albert Einstein with his blackboard. And in one of these blackboards, he wrote his equations for general relativity. This one I'm not going to explain. And in another blackboard, he added something that might be there, perhaps. Now, it turns out that the equations in the lower part of the transparency of the slide explain the orbits of the planets, the existence and behavior of black holes, the gravitational waves, the entire expanding universe, and the one on the upper panel can be one explanation, the best, simplest explanation, of the fact that at the moment, the universe is not only expanding, but it's expanding at an accelerated pace. Now, I'm not going to explain these equations because they are known to everybody. Here you can find them, for instance, in a desert in Bolivia. And one of the very peculiar things that these equations imply is that time is relative. That is to say, time is not something that goes tick-tack everywhere in the universe, but it depends on things. And such knowledge is actually used in GPS satellites, because in 1905, Einstein taught us that an object that is moving relative to you has its clocks, as seen by you, tick slower. And in 1915 or 1916, Einstein invented what's called the general theory of relativity, which predicts correctly that when gravity is weaker, clocks run faster. And interestingly, these two things must be taken into account for GPS satellites to work properly. The GPS satellite computer knows about general relativity. Now, another question is, would someone not doing basic science have made the inventions that I have mentioned? And for instance, the protocol for the basis of the World Wide Web. even without patenting it. Now, the answer to the question above is no. And in other cases, the answer is also no. For instance, if you have an ancient artilleryman trying to improve the aim of his cannons, I doubt it that he would have invented Newton's laws of motion and gravitation. If you have someone working at a telephone company trying to improve communications, I doubt it that he or she would have invented Max's laws of electromagnetic waves, light, and radio communications. And so perhaps some other people who are not basic scientists could have made these discoveries, but it was never the case. Now, let's go to climate and global warming, which is one of the things in which the organizers of this webinar are most interested. And I'm going to talk about climate at CERN, also once again, because, sorry, it's what I know best. Some years ago, an intergovernmental panel on climate change stated that the temperatures were to rise up to 1.5 or 4.5 degrees centigrade for a doubling of carbon dioxide in the atmosphere, which is expected around 2050. Now, one of the main reasons for this large uncertainty is a poor understanding of aerosol particles in the atmosphere and their effects on clouds. As it happens, higher concentrations of aerosol particles make clouds more reflective and more long-lived, cooling the climate, which is the opposite of an increase in CO2 concentration. Now, cloud data from this experiment have been used to build a model of aerosol production based exclusively on laboratory experiments. And what you see in here on the left are observations as a function of latitude at different altitudes, and in the right-hand side is the model. Now, this doesn't look like a perfect prediction, but I can assure you it's much better than what one could do before. This is a comparison, as I said, of modeled and measured particle concentrations versus latitude and altitude, with the latter, the predictions, based only on measurements by cloud. Now, the cloud experiment is what you see in here, and doesn't look like much. And this is an artist impression of it, where you see aerosol particles that are injected in it at different temperatures and degrees of humidity and ionization, etc., in order to understand how aerosols affect clouds and therefore climate. There's another thing which is very important, is being studied by this experiment, and that is cosmic rays. Cosmic rays are things that fall on us from the galaxy and from the sun, and they ionize the atmosphere when they go through. And we are now in a solar cycle, which is variable with an 11 years period. We are at a minimum, and that will also affect the amount of cosmic rays coming from the sun. And it is very interesting, important, essential to know how these cosmic rays affect clouds and therefore climate. And that's one thing that is being done. Now again, this is another estimate by me of the status of the audience at the moment, when I am only about 20% from the end of this webinar.
We need to speed up, Álvaro, a little bit. Sorry.
Okay, I am speeding up. Here are you telling me that I am to speed up. There are people, evil people, asking questions that I don't like sometimes because they are asked not very nicely. Like, what are basic research laboratories such as Fermilab, SLAG, Brookhaven, others in other places, and CERN doing about the coronavirus? The short answer is that they do all they can. And I am going to tell you what CERN has done. The others have done very similar things. The systems used to regulate gas flows for particle physics detectors have been used to design a ventilator that can be used for patients in mild or recovery phases, enabling the high-end machines to be freed up for the most intensive cases. The first prototypes were built, were available at the end of March. They are inexpensive, and they have a control software which is very tiny and will enable the deployment of this ventilator in areas with limited resources and unstable power distribution, that is to say, poor areas. This will allow these objects to be powered with batteries and solar panels or emergency power generators. And my colleagues at CERN found the support of clinicians and international organizations to test their products in hospital settings. This is this respirator being constructed. This is how it would look like. It looks like when it is assembled, and it's powered by a microcomputer and a microcontroller that are really tiny and use very, very little energy. But CERN has also done very many other things, pictured in here. It has handmade face shields at a rate of 1,000 a day, maybe 15,000 in total. It has made about 10,000 liters of sanitizer gel, that is to say 100,000 bottles with a recipe recommended by WHO. It has made protective perspex panels for the logical police stations, and it has made available its vast computing resources and simulations. Now, Carlos, I reached the conclusions. Be happy. The conclusions are not mine. I think they are self-evident. The first one is that basic science is the second best investment. The first best investment is, of course, good education at all levels. This is a long-range but essential investment. And investment in the arts, education in the arts and sciences, respectful of nature, like, not unilaterally nationalistic or otherwise sectarian. Now, this is the second part of my conclusions. You have someone who got lost in a balloon, and he reaches close to a hill, and I can't see very much where he is. So he says to the other guy who's there, I can't see where I am. To which the guy answered, roughly 2.13 meters above my head. You must be a scientist. Why? Because your answer was slow, very precise, and totally useless. And the hope of my talk today is that you have all understood that this is fake news. And I think this is a point, I know this is a point, it's a very good point for me to stop, and we may go, if you so would, to questions and answers.
Thank you very much, Alvaro. I have even myself understood your speech, so I'm sure that the rest of the almost 525 persons that engage have followed you well. It is clear that we are at a time of a dual crisis, the COVID-19 and the climate change crisis. The first one is acute and immediate, while the second, although slower, it's equally critical. The two crises have clearly interlinked because the scale and nature of economic policy decisions being made now that will be crucial and will affect climate outcomes far in the future. The time to act is now, and the decisions that we take now will shape economies and the global system for decades. Policymakers will rightly focus on protecting public health, stabilizing economies, and helping those whose livelihoods are at stake. But if the recovery from the crisis is to be sustainable, if our world is going to become more resilient, we must do everything in our power to promote recovery. And basic science, as you well mentioned, Alvaro, should be accelerated. And investment in basic science is very much needed for this. Now, question and answers and wrap-up will be done by my colleague Martin Dasek, IFC Financial Institution Group, Europe and Central Asia, Senior Climate Specialist and Advisory Lead. Martin, over to you.
Thank you, Carlos. And of course, thank you, Alvaro, for great presentation. And thank all for great participation. We have about 500 participants online. We have got many questions. I think we can divide them in two groups. One is more concrete about Higgs particles and about the presentation title, and the other ones are more general. So I will start with the with the detailed one. And one question is about if the Higgs field is everywhere, what is its relation to vacuum and the structure of space-time? Alvaro, are you able to shortly describe?
Yes, in fact, there is no vacuum in the universe. There is no vacuum because the Higgs field permeates the vacuum everywhere. And its relation to the expansion of the universe is not well understood. And therefore, the answer will be too long, and I'm not going to give it.
Okay.
We don't know, so we must continue basic research.
Thank you. The other question, you already touched upon it. It's about relation about the basic science and real use. And when electron was discovered, who could imagine the electronic world we have today? What do you think that in the future Higgs particles could play such a role? And if so, what is your expectation in this respect?
Well, Higgs particles will definitely not play such a role because, as I stated, they last too little. There are no Higgs particles in your atoms. There are no Higgs mines that you can go and pick them up. And electrons, on the other hand, are stable. As far as we know, electrons cannot decay into anything, cannot be disintegrated. And electrons are indeed the basis of electronics, and electronics is the basis of something like industries in the world use electronics somehow, if not more.
Thank you very much. So now there are questions regarding to science as such. Can you please give your opinion on how to best advocate the importance of basic science to non-scientific publics? Should this be a priority since there is a crescent trend for public involvement in public policies regarding science, including funding? So that's the question.
Well, my opinion is that the first thing about the public in general is that we all should be educated better. Once we are all educated better, the evidence that doing basic science is useful for mankind will become more and more obvious. And that's briefly said what I think. We need basic science. We need much better education.
Completely true. Thank you. So, in your view, Mr. Professor, is this pandemic crisis going to change people's, companies, and investors' mindset? And as a result, they will put more attention and resources to fundamental science, fostering groundbreaking scientific discoveries? Is this going to happen? Hopefully.
Well, if it is to happen, one of the things we have to do is to have nice people like you allow scientists to express their views on basic science. And in the case of virology, this has become quite obvious. There is no question that genetics and virology and medicine will get a fraction of the support that they need. The question is whether other basic sciences will get equally stronger support, and that's an entirely open question. I wish this will happen. I wish scientists managed to speak in a way to politicians, and I wish politicians would listen. That's a wish.
Yeah, thank you. And this actually leads to the question which is linked that we are organizing this webinar on behalf of World Bank. And what is, in your opinion, relationship between the financial world and basic science? How can those two worlds work together?
Well, I must say that I am totally ignorant about the financial world. So my opinion, this is a very good question, which is what one says when one doesn't know what to answer. This is a very good question. And let me narrow down what you mean by finances. Suppose you are talking about Wall Street. That, to a scientist, seems to be a contradiction of basic laws of nature, like the law of energy conservation, because Wall Street doesn't produce anything. And in spite of that, it produces wealth for some people. Clearly, a conservation law must be there. It's only that the wealth is transmitted from those who are not so rich to those who are already very rich. Now, another aspect of finances, I will narrow it down to the people who have a lot of money. And some of these people, fortunately, are continuously, and at the moment in particular, doing a lot of good. For instance, the Bill and Melinda Gates Foundation. Now, how do you know that they are doing very good? Because the people who spread fake news and fight against anything which is good make such extraordinarily effort to belittle what the Gates Foundation is doing, that it becomes obvious that the Gates Foundation is doing something very good. There are many such foundations, like the Simons Foundation, that works in things from life sciences to mathematics and mathematical physics. You may say, what's mathematics good for? Well, if Leibniz, yes, and Newton had not invented differential calculus, we could not calculate practically anything except by adding and subtracting things. There's a big tradition in the United States of rich people supporting good causes. There is, for instance, the Rockefeller Foundation, which is, I think, something like a century old, and there are many other foundations. For instance, there's one called the Alfred Sloan Foundation that gives fellowships to people. I once had one of their very generous fellowships for 2 or 3 years, and in that particular case, my own opinion is that they did not waste their money, but I think that's perhaps only my own opinion.
Thank you very much. And I if you nicely summarized the key messages which we were hoping to spread out today. Because we believe, of course, the current situation affected by pandemic will somehow finish soon. But as you mentioned, there is the wish, and we hope that we will find ourselves in a slightly different world. And of course, we still need to be worried about the continuation of the support for basic science, not currently related to medicine, biology, virology, and so on. And as we have heard, we need the basic science for developing other things we have today. So we still believe that basic science should have and shall continue contributing to rebuild a more dynamic and resilient society, and hopefully more sustainable and competitive economic model that brings more opportunities for all. And I believe with this we can end today. And I'm passing to Carlos for final remarks, if you allow me.
Thank you very much, Martin, and thank you so much, Alvaro, Martin, and the audience for attending this Ctrl+Alt+Delete Green Rebuild #2 webinar. I think it has been very interesting. We had a lot of attention up to the end. Right now, with 422 persons connected. Thank you all of you. And I would like to mention that all participants are going to receive an email tomorrow that will include a small little survey to be completed as a useful way for you to give us some opinion and recommendations. And we will also include in that email an invitation and registration link for our next Ctrl+Alt+Delete Green Rebuild webinar that will be COVID and the New World Order, Green Economy, the Great Opportunity. In that occasion, we will be hosting Juan Verde, who was the former advisor to President Clinton and Obama, and also Vice President Al Gore, and now he's on the team as one of the main pillars for candidate Joe Biden. So thank you very much to everyone. I have enjoyed very much this webinar, Alvaro. Thank you so much. I hope you have also do it. And let's go for a green rebuild. Thank you.